Picture this. Right now, as you settle into this moment of quiet contemplation, there's an ancient wanderer racing through our solar system at 130,000 miles per hour. It's been travelling for 8 billion years, twice as old as Earth itself, carrying secrets from the depths of interstellar space. And yet, this cosmic visitor named 3 Atlas poses absolutely no threat to us. The real nightmare isn't what's coming from the stars, it's what's already here, hidden in plain sight, waiting patiently in the darkness between worlds. Welcome to another journey through the cosmos, where we'll explore not just the vastness of space, but the intimate relationship between our fragile planet and the forces that shape our existence. I'm glad you're here, settling in for what I hope will be a peaceful voyage through some of the most profound questions our universe has to offer. Tonight, we're going to unpack a beautiful paradox. How can something travelling faster than any interstellar object we've ever observed be completely harmless, while the real threats lurk much closer to home? It's a story that begins with wonder and ends with a deeper appreciation for just how remarkable our survival truly is. Let me paint you a picture of 3I Atlas, this remarkable visitor that's captured the attention of astronomers worldwide. Discovered on July 1st, 2025, by the Atlas Survey Telescope in the Chilean desert, this interstellar comet represents only the 3rd confirmed visitor from beyond our solar system that we've ever detected. Think about that for a moment. In all of human history, with all our telescopes and technology, we've only identified 3 objects that originated from other star systems. The name itself tells a story. The I stands for interstellar, marking it as a cosmic immigrant. The 3 reminds us how rare these encounters truly are. And Atlas? That's the telescope system that found it, scanning the heavens night after night, watching for objects that might threaten our world. But here's what makes 3I Atlas so fascinating. It's moving at speeds that almost defy comprehension. 130,000 miles per hour. To put that in perspective, if you could travel at that speed, you could circle the Earth's equator in about 12 minutes. It's the fastest interstellar object ever recorded, a cosmic bullet that's been gathering momentum for billions of years as it danced between the gravitational wells of distant stars and nebulae. And yet, despite this tremendous velocity, despite its ancient origins in the depths of space, 3I Atlas will never come closer than 150 million miles from Earth. That's roughly the same distance that separates us from the Sun. In cosmic terms, it's practically waving hello from the neighbourhood sidewalk, rather than barging through our front door. The Hubble Space Telescope has given us our clearest glimpse of this visitor. What it revealed is poetry in motion, a teardrop-shaped cloud of dust, a luminous coma stretching nearly 12,000 miles across, and a delicate tail streaming behind it like cosmic silk. It's beautiful, ethereal, and completely benign. Scientists estimate that 3I Atlas measures somewhere between 1,400 feet and 3.5 miles across. Even at the larger estimate, it's a mere pebble compared to the objects that have genuinely threatened our planet throughout history. But its composition tells an intriguing story. Early observations suggest it has one of the highest ratios of carbon dioxide to water ever recorded in a comet, hinting at formation conditions unlike anything in our solar system. This ancient wanderer began showing activity when it was still over 6 astronomical units from the Sun, much farther out than most comets start their spectacular displays. It's as if 3I Atlas is so eager to perform that it began its cosmic dance long before reaching centre stage. But perhaps the most remarkable thing about 3I Atlas isn't its speed or its composition, or even its interstellar origins. It's what it represents, a gentle reminder that the universe is vast beyond imagination, filled with wonders that pose no threat to us whatsoever. It's a cosmic postcard from regions of space so distant that light from those areas takes thousands of years to reach us. Now, let's shift our perspective from this harmless visitor to contemplate what real cosmic threats actually look like. Because while 3I Atlas races harmlessly through our solar system, there are other objects, much closer to home, that have fundamentally shaped the history of life on Earth. 66 million years ago, our planet experienced what can only be described as the ultimate nightmare scenario. It wasn't a visitor from interstellar space. It was something much more mundane, much more local, and infinitely more devastating. An asteroid roughly 6 miles across slammed into what is now the Yucatan Peninsula at speeds of about 45,000 miles per hour. To understand the scale of this catastrophe, imagine trying to comprehend the energy release. The Chicxulub impact, as it's now known, released the equivalent of 100 trillion tons of TNT. That's more than 1 billion times the energy of the atomic bombs dropped on Hiroshima and Nagasaki combined. It was, quite literally, an explosion that reshaped the world. But the impact itself was just the beginning of the nightmare. The asteroid didn't simply create a crater and call it a day. It initiated a cascade of environmental disasters that would make any modern climate crisis seem manageable by comparison. First came the immediate devastation. The impact vaporized the asteroid and a significant portion of the Earth's crust at the impact site, creating a crater 120 miles across and 19 miles deep. The shockwave from this collision traveled around the globe, triggering massive earthquakes and volcanic eruptions thousands of miles away. Then came the atmospheric catastrophe. The impact hurled billions of tons of debris into the atmosphere, along with vaporized sulfur-rich rocks that created a global haze of sulfuric acid droplets. This wasn't just dust settling after a construction project. This was a planetary shroud that blocked sunlight for months, possibly years. Picture the Earth during this time, a world where noon looked like twilight, where temperatures plummeted as photosynthesis ground to a halt. Plants withered and died in the perpetual gloom. Herbivores starved as their food sources disappeared. Carnivores followed as their prey vanished. It was a domino effect of extinction that claimed 75% of all species on Earth, including the mighty dinosaurs who had ruled the planet for over 160 million years. The truly haunting aspect of the Chicxulub impact is how swiftly it transformed a thriving, biodiverse world into a post-apocalyptic wasteland. Geological evidence suggests that the mass extinction happened rapidly, perhaps within just a few thousand years. In geological terms, that's essentially instantaneous. And here's what should give us pause. The asteroid that caused all this devastation was only about twice the size of 3I Atlas at its largest estimate. The difference wasn't necessarily the size of the impactor, but rather its trajectory, its composition, and most crucially the fact that it actually hit us. But we don't need to reach back 66 million years to understand the potential for cosmic catastrophe. On a quiet morning in June 1908, the skies over Siberia provided a more recent, and in some ways more unsettling, demonstration of what happens when Earth encounters even a relatively small cosmic visitor. The Tunguska event, as it came to be known, began like something from a fever dream. Witnesses across the sparsely populated region reported seeing a brilliant fireball streak across the early morning sky, brighter than the sun itself. What followed was an explosion that flattened over 800 square miles of forest, an area larger than some small countries. The object responsible for this devastation was likely only about 160 to 200 feet across, smaller than many city blocks. It never even reached the ground. Instead, it exploded in the atmosphere about 6 miles above the Earth's surface, releasing the equivalent of 4 megatons of TNT. That's roughly 250 times more powerful than the atomic bomb dropped on Hiroshima. The Tunguska explosion knocked down an estimated 80 million trees, arranged in a radial pattern that's still visible in satellite images today. The shockwave was felt hundreds of miles away. Windows shattered. People were knocked off their feet. The atmospheric disturbance was so significant that it caused unusual twilight glows across Europe and Asia for several nights afterward. But perhaps the most chilling aspect of the Tunguska event isn't what happened, But what could have happened? If that same object had arrived just a few hours later, as Earth's rotation carried populated areas into its path, it might have detonated over St. Petersburg or another major city. The death toll would have been catastrophic. Scientists estimate that Tunguska-sized events occur roughly once every 300 to 1,000 years. That might seem reassuringly infrequent, but consider this: we're overdue. It's been over a century since Tunguska, and our planet is much more densely populated now than it was in 1908. Imagine a Tunguska-scale explosion centered over London, New York, Tokyo, or any major metropolitan area. The immediate death toll would likely be in the millions. The economic disruption would be global. The psychological impact would be profound, a sudden and undeniable reminder of our cosmic vulnerability. And yet, the object that caused Tunguska was insignificant compared to the Chicxulub impactor. It was a cosmic pebble, barely large enough to register on our threat assessment scales. But it was moving fast, and it was in exactly the wrong place at exactly the wrong time. If Tunguska feels too distant, too much like ancient history, let me bring you into the present century with a story that unfolded on February 15th, 2013, above the Russian city of Chelyabinsk. It was a Friday morning, and people were going about their daily routines when the sky suddenly blazed with light. Dashboard cameras, ubiquitous in Russian vehicles, captured the moment from dozens of angles as a brilliant fireball streaked overhead, casting shadows in broad daylight. The Chelyabinsk meteor was relatively small, only about 60 feet across, but it was moving at over 42,000 miles per hour when it entered our atmosphere. The explosion, equivalent to about 440,000 tons of TNT, occurred 14 miles above the ground. What made Chelyabinsk particularly unsettling wasn't the explosion itself, but what it revealed about our preparedness. Nobody saw it coming. Despite all our telescopes, all our tracking systems, all our early warning networks, this house-sized rock approached from the direction of the sun and remained completely undetected until it was already exploding in our atmosphere. The shockwave from the explosion blew out windows across 200 square miles. Over 1,600 people were injured, mostly from flying glass. Buildings were damaged. The psychological impact was immediate and profound as people realized how helpless they were in the face of cosmic forces they never saw approaching. But here's what should really give us pause. Chelyabinsk was small. It was a cosmic dust mote compared to the objects that have shaped Earth's history. And yet it served as a stark reminder that space is full of objects we're not tracking, objects that could arrive without warning. The asteroid that created the Chelyabinsk event was part of a population of near-Earth objects that astronomers call city killers. They're too small to cause global devastation, but large enough to devastate urban areas. Scientists estimate there are hundreds of thousands of these objects in Earth-crossing orbits, and we've only identified a small fraction of them. Every year, our planet is hit by dozens of smaller meteors that burn up harmlessly in our atmosphere. Most pass unnoticed except by dedicated observers and automated detection systems. But occasionally, as Chelyabinsk demonstrated, something large enough to cause real damage slips through undetected. This brings us to one of the most unsettling aspects of the cosmic threat: the sheer number of objects we haven't found yet. While 3i Atlas announces its presence with a brilliant comet and tail racing through our solar system in full view of our telescopes, the real threats are often invisible until it's too late. Current estimates suggest there are over 25,000 neroids larger than 4 Earth asked 150 feet across. Objects this size could devastate entire regions, creating destruction comparable to major nuclear weapons. Yet we've only catalogued about 40% of them. The rest remain hidden in the vast darkness of space, following orbits that may or may not intersect with Earth's path around the Sun. The detection challenge is more complex than you might imagine. Unlike comets, such which announce themselves with GL as 3i Atlas, owing comas and streaming tails, asteroids are typically dark, rocky objects that reflect very little sunlight. They're cosmic stealth bombers, invisible until they're close enough to pose an immediate threat. Many dangerous asteroids spend most of their time in the glare of the sun, making them nearly based telescopes. Others approach impossible to detect from Earth from directions where our surveillance coverage is limited. Still others are so dark that they barely register against the star-filled background of space. In April 2018, an asteroid possibly as wide as 3 to Earth and the Moon. It was 160 feet past closer detected until after it had already made its closest approach. This wasn't a failure of our detection systems. It was a reminder of their limitations. Consider what this means. Right now, as you listen to these words, there are thousands of objects large enough to cause regional devastation, following orbits that regularly bring them near Earth. Most of them remain unknown, untracked, and unpredictable. The truly massive objects, the planet killers, comparable to the Chicxulub impactor, are somewhat easier to detect due to their size. But even here, our catalogue is incomplete. Scientists estimate that hundreds of objects larger than a mile across remain undiscovered in near-Earth space. And then there are the dark comets, a newly recognized category of objects that combine the worst characteristics of both asteroids and comets. They're small, fast-moving, and nearly impossible to detect. Unlike traditional comets, they don't develop the bright comas and tails that make them visible from great distances. Unlike asteroids, their orbits are unpredictable and unstable. These dark comets may represent a significant blind spot in our planetary defense strategies. They could approach from unexpected directions, accelerate or decelerate unpredictably, and remain invisible until they are already in our neighborhood. The statistical reality is both comforting and terrifying. The chance of a civilization-ending impact in any given year is roughly 1 in 300,000. Those are odds that most of us would happily accept for almost any other risk. But the consequences of being wrong are so absolute, so final, that the small probability takes on an outsized psychological weight. To truly understand why 3i Atlas is harmless, while other cosmic visitors pose genuine threats, we need to examine the physics of impact events. It's not just about size, though. Size certainly matters. It's about velocity, composition, angle of approach, and the specific characteristics of both the impactor and the target. When objects collide in space, the energy released increases with the square of the velocity. This means that a comet traveling at 60,000 miles per hour doesn't just pack twice the punch of an asteroid moving at 30,000 miles per hour. It carries 4 times the destructive energy. Speed in cosmic terms is everything. This is why comets, despite being composed largely of ice and dust rather than solid rock, can be far more dangerous than similarly sized asteroids. Comets typically approach Earth at much higher velocities because they're falling in from the outer solar system, accelerated by the sun's gravity across vast distances. The angle of approach also matters tremendously. An object that strikes Earth head-on, perpendicular to the surface, delivers its energy most efficiently to the target. A glancing blow, while still potentially devastating, disperses some of its energy across the atmosphere rather than concentrating it at the impact site. The composition of the impactor determines how much of its energy actually reaches the surface. Rocky asteroids tend to survive atmospheric passage better than icy comets or loosely bound rubble piles. Iron-rich asteroids are particularly dangerous because they're dense and coherent enough to punch through the atmosphere with minimal energy loss. But perhaps most importantly, the location of impact dramatically affects the consequences. An ocean impact, while potentially generating devastating tsunamis, doesn't inject as much debris into the atmosphere as a land impact. A strike in a remote area causes regional damage but leaves global civilization intact. A direct hit on a major population center would be catastrophic regardless of the object's size. The Chicxulub impactor struck at what scientists now recognize as nearly the worst possible location. The Yucatan Peninsula's bedrock is rich in sulfur-bearing minerals that vaporized upon impact, creating the global atmospheric haze that prolonged the environmental catastrophe. A similar impact in a different geological setting might have caused less long-term damage. This brings us back to 3I Atlas and why it represents no threat whatsoever. Its trajectory carries it safely past Earth at a distance that eliminates any possibility of collision. Its composition, while unusual, is typical of comets, mostly ice and dust rather than dense, rocky or metallic material. And its speed, while impressive, is directed away from Earth rather than toward it. In essence, 3I Atlas is a cosmic reminder of what benign celestial mechanics look like. It's vast, ancient and beautiful, but it's also harmless precisely because its orbit doesn't intersect with Earth's position in space. The real nightmares are the objects we haven't found yet, the ones following Earth-crossing orbits, the ones that could arrive with little or no warning. They're not necessarily larger or faster than 3I Atlas, they're just pointed in the wrong direction. As we drift deeper into this cosmic contemplation, consider how remarkable it is that we exist at all. Our planet has been struck by countless objects throughout its history, yet here we are, conscious beings capable of detecting and studying these threats. We've survived the cosmic lottery for billions of years, and our growing understanding of these processes gives us hope that we might continue to do so. But our journey through the architecture of cosmic catastrophe is just beginning. In our next exploration, we'll delve into the hidden mechanisms that govern these collisions, the secret patterns that determine which objects become harbingers of doom and which pass by as harmless visitors. Because the story of 3I Atlas isn't just about one comet's journey through our solar system. It's about the invisibled our fragile civilization to flourish in a universe full of both wonder and peril, forces that shape the fate of worlds, and the remarkable chain of circumstances that have allowed. There's something almost mystical about the way celestial mechanics operate, like a vast clockwork mechanism that's been ticking away for billions of years with a precision that would make the finest Swiss watchmaker weep with envy. And yet, within this apparent order lies a beautiful chaos, a dance of gravitational influences that determines whether 3I Atlas pass objects like by peacefully or become harbingers of destruction. Consider the delicate balance that governs our cosmic neighborhood. Every object in the solar system, from the tiniest grain of dust to the most massive planet, exists within an intricate web of gravitational relationships. Jupiter, our solar system's gentle giant, acts as both protector and threat. Its immense gravity field sweeps up many potentially dangerous objects, flinging them out of the inner solar system like a cosmic goalkeeper. But occasionally, Jupiter's influence works in reverse, deflecting objects into Earth-crossing orbits that wouldn't otherwise threaten us. The asteroid belt, that ring of rocky debris between Mars and Jupiter, tells a similar story of cosmic near misses. Most of these objects remain safely confined within their orbital lanes, held in check by Jupiter's gravitational influence. But gravitational resonances, those subtle mathematical harmonics that govern orbital mechanics, occasionally nudge asteroids out of their stable paths and add into the inner solar system, process that unfolds over millions of years, invisible to human perception, but relentlessly persistent. An asteroid might orbit peacefully for eons before a chance gravitational encounter with Mars or Jupiter slightly alters its path. That tiny change, perhaps amounting to just a few meters per second, might be enough to transform a harmless space rock into a potential Earth crosser centuries or millennia later. The Yarkovsky effect adds another layer of complexity to this cosmic choreography. Named after a Russian engineer who first described it, this phenomenon occurs when asteroids absorb sunlight and re-radiate it as heat. The slight pressure from this thermal radiation can gradually alter an asteroid's orbit over long periods. It's an incredibly subtle force, like trying to push a car by blowing on it, but given enough time, it can dramatically change an object's trajectory. This is why asteroid tracking is such a challenging endeavour. It's not enough to simply catalogue where objects are today. Scientists must calculate their future positions decades or even centuries in advance, accounting for all these subtle gravitational and thermal influences. A small error in measurement or an unknown perturbation can make the difference between predicting a safe passage and missing a potential impact. The case of asteroid Apophis illustrates this challenge perfectly. When first discovered in 2004, calculations suggested a small but significant chance that this 1,000-foot wide asteroid might strike Earth during its close approach in 2029. The uncertainty was maddening. Here was an object large enough to devastate a continent, and scientists couldn't definitively say whether it would hit us or miss us by thousands of miles. Fortunately, continued observations and refined calculations eventually ruled out any least the next century. But the episode impact threat from Apophis, for it highlighted how even our best efforts to predict cosmic trajectories carry inherent uncertainties. While we focus our attention on near-Earth asteroids and the occasional interstellar visitor like 3I Atlas, there's a vast reservoir of potential threats lurking at the very edge of our solar system. The Oort cloud, named after Dutch astronomer Jan Oort, is a spherical shell of icy objects that extends nearly halfway to the nearest star. Picture this immense structure, a sphere containing perhaps 1 trillion comets, each one a potential visitor to the inner solar system. Most of these objects have remained frozen in deep space for billions of years, so distant from the Sun that they receive virtually no heat or light. They're cosmic time capsules, preserving the primordial materials from which our solar system formed. But occasionally, something disturbs this distant tranquility. The passage of a nearby star, the gravitational influence of the galaxy's spiral arms, or even the subtle tug of massive molecular clouds can nudge Oort cloud objects into long elliptical orbits that carry them toward the inner solar system. These long-period comets represent a particularly insidious threat because they're essentially impossible to predict. Unlike the near-Earth asteroids that follow relatively stable, well-understood orbits, long-period comets can arrive from any direction with little warning. They might be invisible until just months before reaching the inner solar system, giving us virtually no time to mount any kind of defensive response. The composition of these distant visitors adds another layer of concern. Oort cloud comets are pristine remnants from the solar system's formation, containing high concentrations of volatile materials that haven't been processed by repeated passages near the Sun. When these objects finally do venture into the inner solar system, they can become spectacularly active, developing enormous comas and tails that make them beautiful to observe, but also potentially more dangerous upon impact. Comet Hale-Bopp, which graced our skies in the late 1990s, originated from the Oort cloud and took over 4,000 years to complete its journey to the inner solar system. It was a magnificent sight, visible to the naked eye for months, but it also served as a reminder of the vast timescales involved in these cosmic processes. The truly unsettling aspect of the Oort cloud is its sheer size and the number of potential projectiles it contains. If even a tiny fraction of these objects were somehow disturbed and sent toward the inner solar system, the result would be a bombardment that would make the late heavy bombardment of 4 billion years ago seem gentle by comparison. Fortunately, such catastrophic disturbances are extremely rare. The gravitational environment at the edge of the solar system is relatively stable, and most Oort cloud objects will remain safely frozen in their distant orbits for the remainder of the Sun's lifetime. But the knowledge that this vast arsenal exists, just waiting for the right gravitational nudge, adds a sobering perspective to our cosmic situation. As we contemplate these vast cosmic forces and ancient impact events, it's worth pausing to consider how humanity itself has begun to alter the equation. We live in what many scientists call the Anthropocene epoch, a time when human activities have become a geological force comparable to natural processes. Our growing technological capabilities have given us, for the first time in Earth's history, the potential to detect and potentially deflect incoming cosmic threats. The DART mission, which successfully altered the orbit of the asteroid Dimorphos in 2022, demonstrated that we're no longer passive victims of cosmic circumstance. We can, in principle, defend ourselves against at least some classes of threats. But this newfound capability comes with its own complexities and ethical considerations. Who decides which objects represent threats worthy of deflection? What are the consequences of altering an asteroid's orbit, potentially sending it toward a different target? How do we balance the immediate safety of Earth against the long-term stability of the solar system? The technology that allows us to detect and track potentially hazardous objects also reveals the scale of our cosmic vulnerability. Every new survey telescope, every improved detection algorithm adds to our catalogue of known threats while simultaneously revealing how much we still don't know. Consider the psychological impact of this knowledge. Previous generations lived in blissful ignorance of cosmic threats, experiencing asteroid and comet impacts as acts of divine intervention or natural catastrophe beyond human understanding. We, in contrast, live with the constant awareness that civilization-ending objects are out there, following predictable orbits that we can calculate centuries in advance. This knowledge brings both empowerment and anxiety. We can prepare for known threats, develop technologies to address them, and make informed decisions about planetary defense priorities. But we also carry the burden of understanding just how precarious our existence truly is. The detection of 3I Atlas and other interstellar objects adds another dimension to this cosmic awareness. These visitors remind us that our solar system exists within a vast galactic community, subject to influences from stellar neighborhoods we can barely imagine. They're harbingers from the deep cosmos, carrying information about stellar formation processes, planetary system evolution, and the chemical composition of distant stellar nurseries. There's a profound philosophical dimension to contemplating these cosmic threats and celestial visitors. The scale of space and time involved in these processes challenges our most basic assumptions about significance, purpose, and meaning. When we consider that 3I Atlas has been traveling through interstellar space for 8 billion years, longer than our planet has existed, we're confronted with temporal scales that dwarf human experience. This ancient wanderer witnessed the formation and death of countless stars, the birth and evolution of planetary systems, the rise and fall of cosmic structures we can only begin to imagine. And yet, here we are, ephemeral beings on a small planet, capable of detecting and studying this ancient traveller. There's something almost miraculous about the fact that atoms forged in stellar cores billions of years ago have organised themselves into patterns complex enough to contemplate their own cosmic origins. The threat of impact events adds urgency to these philosophical reflections. The knowledge that a chance encounter with a cosmic projectile could end human civilization within minutes or hours forces us to confront questions about the ultimate meaning and purpose of our existence. Are we simply cosmic accidents, brief patterns of organisation in an otherwise indifferent universe? Or does our ability to understand and potentially defend against these threats suggest some deeper significance to consciousness and intelligence? The dinosaurs ruled Earth for over 160 million years before the Chicxulub impact ended their dominance. Human civilization, by contrast, has existed for mere millennia. We've developed the ability to detect cosmic threats in just the last few decades. If we can avoid catastrophic impacts for even a few more centuries, we might become the first species in Earth's history to achieve genuine cosmic security. This possibility carries both promise and responsibility. We might be approaching a transition point where intelligence becomes a significant force in cosmic evolution, where conscious beings can actively shape the trajectory of life rather than simply responding to environmental pressures. But achieving this cosmic maturity requires more than just technological capability. It demands wisdom, cooperation, and a long-term perspective that extends far beyond the typical horizons of human planning. we must learn to think in geological timescales while acting decisively in the present moment. Beneath the apparent randomness of cosmic impacts lies a subtle but persistent rhythm, patterns that emerge when we examine impact events across geological timescales. Some scientists have proposed that major extinction events occur with a periodicity of roughly 26 to 30 million years, suggesting that our solar system's motion through the galaxy might influence the frequency of cosmic bombardments. As our solar system orbits the galactic center, it oscillates up and down through the galactic plane like a horse on a cosmic carousel. This motion carries us through regions of varying stellar density, gravitational fields, and perhaps most significantly, clouds of dark matter that might disturb the outer regions of the solar system. During passages through the galactic plane, where stellar density is highest, gravitational perturbations might be more likely to dislodge objects from the Oort cloud and send them careening toward the inner solar system. These disturbances wouldn't produce immediate effects. The journey from the Oort cloud to the inner solar system takes millions of years, but they might create periodic waves of comet showers separated by relatively quiet intervals. The evidence for this galactic influence remains controversial, with some scientists arguing that the apparent periodicity in extinction events is merely a statistical artifact. But the possibility that our planet's bombardment history is linked to our galaxy's structure adds another layer of complexity to the cosmic threat assessment. Even more intriguing is the suggestion that nearby stellar events might influence our cosmic environment. Supernovae, those spectacular stellar explosions that occur when massive stars reach the end of their lives, can strip away portions of the Oort cloud or alter the orbits of objects within it. A supernova within 50 light-years of Earth might not only expose our planet to dangerous radiation, but also trigger a bombardment of comets and asteroids that could persist for millions of years. The good news is that there are no supernova candidates in our immediate stellar neighborhood. The nearest massive star capable of exploding as a supernova is over 100 light-years away, far enough that its death throes would be spectacular, but not immediately threatening. But these cosmic connections remind us that Earth exists within multiple nested systems of influence. We're not just orbiting the Sun in isolation. We're part of a stellar neighborhood that's embedded within a spiral arm of a galaxy that's itself moving through an expanding universe. Events occurring on any of these scales can potentially influence the cosmic environment that shapes life on Earth. One of the most humbling aspects of cosmic impact threats is their fundamental democracy. When a large asteroid or comet strikes Earth, it doesn't discriminate based on nationality, wealth, political system, or any other human distinction. The environmental consequences are global, affecting all life regardless of its location or circumstances. This universal vulnerability has important implications for how we approach planetary defense. Unlike most other existential risks, cosmic impacts require genuinely global cooperation to address effectively. No single nation, no matter how technologically advanced, can mount an adequate defense against large impact threats. The detection networks, deflection technologies, and coordination mechanisms necessary for planetary defense must be international efforts. The political and economic challenges of organizing such cooperation are immense. How do you coordinate response efforts across nations that may be political rivals? How do you fairly distribute the costs of planetary defense systems? What happens when deflection efforts succeed for some regions but potentially redirect threats toward others? These questions become more complex when we consider that the lead times for addressing cosmic threats can span decades or even centuries. Political systems, international alliances, and economic arrangements that seem stable today may be completely transformed by the time we need to implement defensive measures against a newly discovered threat. The history of international cooperation on global challenges offers both hope and caution. The Montreal Protocol's success in addressing ozone depletion demonstrates that humanity can coordinate effectively when faced with clear environmental threats. But the ongoing struggles with climate change, despite overwhelming scientific consensus about its dangers, illustrate how difficult it can be to maintain cooperation when the timeline for action spans multiple generations. Cosmic impact threats occupy a unique position in this spectrum of global challenges. They're potentially more catastrophic than climate change, but also more distant and abstract for most people. A threatening asteroid might be decades away from its closest approach to Earth, making it difficult to maintain public attention and political commitment over such extended periods. As our understanding of cosmic threats has grown, we've encountered a fascinating paradox. The more we learn about the frequency and potential consequences of impact events, the more we realize how remarkably fortunate Earth has been throughout the history of complex life. Major impact events capable of causing mass extinctions occur roughly every 50 to 100 million years. But the evolution of complex life, particularly the development of large, sophisticated organisms, has proceeded largely uninterrupted for over 500 million years. This suggests either remarkable luck or perhaps some protective mechanism we don't fully understand. Some scientists have proposed that Jupiter's gravitational influence provides a partial explanation for this apparent protection. By capturing or deflecting many incoming objects, Jupiter may have reduced the impact flux in the inner solar system to levels that allow complex life to flourish. Without this giant planet standing guard, Earth might have experienced a much more violent bombardment history. But Jupiter's protection is imperfect, as the Chicxulub impact demonstrates. And there are scenarios where Jupiter's influence might actually increase rather than decrease impact threats. Computer simulations suggest that the giant planet's gravitational perturbations might occasionally send objects into Earth-crossing orbits that would otherwise remain safely in the outer solar system. This uncertainty about our cosmic protection mechanisms adds another layer of complexity to threat assessment. We know that major impacts have occurred in Earth's past and will certainly occur in the future, but we can't predict with confidence whether the current relatively quiet period will continue for millions more years or end tomorrow. The development of technological civilization has occurred during what appears to be a particularly benign period in Earth's cosmic bombardment history. The last major impact event occurred 66 million years ago, long before the emergence of human ancestors. We've had the luxury of developing science, technology, and global communication networks without facing immediate existential pressure from cosmic threats. But this benign environment may be ending. Our improved detection capabilities are revealing the true scope of the cosmic threat environment, showing us thousands of potentially hazardous objects that previous generations never knew existed. We're transitioning from ignorance to awareness, and that transition brings both opportunities and responsibilities. The question facing our species is whether we can develop adequate defensive capabilities before encountering a truly threatening object. It's a race between technological development and cosmic chance, with the future of human civilization potentially hanging in the balance. And yet, as we contemplate these vast uncertainties and potential catastrophes, there's something profoundly hopeful about our situation. For the first time in Earth's history, a species has developed the ability to see these threats coming and potentially do something about them. We're no longer passive victims of cosmic circumstance. 3i Atlas, racing harmlessly through our solar system, represents both the beauty and the benevolence that the universe can offer. It reminds us that not every cosmic visitor brings destruction. Sometimes they bring wonder, knowledge, and a deeper appreciation for the remarkable cosmic dance in which we all participate. As we prepare to explore the deeper implications of our cosmic awareness, consider how this ancient interstellar wanderer has already changed us simply by being observed. Every photon of light we've captured from 3i Atlas carries information from the depths of space and time, adding to our understanding of stellar formation, planetary system evolution, and the chemical composition of the cosmos. But the story we've been telling about cosmic threats and celestial visitors is really a story about something much more fundamental: the relationship between knowledge and vulnerability, between awareness and anxiety, between scientific discovery and existential responsibility. And that story is far from over. In our continuing journey through these cosmic mysteries, we'll need to examine not just what threatens us from space, but what our growing awareness of these threats reveals about the nature of consciousness, intelligence, and our place in the universe. Because the real question isn't whether 3i Atlas is harmless. The real question is whether we can learn to live with the knowledge of what isn't. There's a curious transformation that occurs when you first truly grasp the scale of cosmic threats surrounding our planet. It's not unlike the moment when a child realizes that their parents don't have all the answers, that the adults who seem so confident and capable are actually navigating uncertainty with the same mix of hope and fear that defines the human condition. We've spent the last few centuries building a civilization based on the assumption of terrestrial stability. Our cities, our institutions, our long-term planning all rest on the quiet belief that tomorrow will be fundamentally similar to today. We build skyscrapers that are designed to last decades, plant trees will never see fully grown, and make promises that extend far beyond our individual lifespans. But cosmic awareness changes this calculus in subtle yet profound ways. Once you understand that a single object, perhaps no larger than a city block, could end human civilization within hours, every human achievement takes on a different character. The pyramids of Egypt, built to last for eternity, suddenly seem both more precious and more fragile. The accumulated knowledge in our libraries, the art in our museums, the relationships that define our lives, all exist within a bubble of cosmic fortune that could burst at any moment. This isn't meant to inspire despair, but rather a different kind of appreciation. When you realize how improbable our continued existence truly is, every sunset becomes more beautiful, every human kindness more meaningful, every moment of consciousness more miraculous. We are living in the narrow gap between cosmic catastrophes, and that gap is filled with wonder. Scientists who work in planetary defense often describe a peculiar psychological adaptation to this knowledge. Initially, the awareness of cosmic threats can be overwhelming, almost paralyzing. The sheer scale of the forces involved, the randomness of their timing, the inadequacy of our current defensive capabilities, all combine to create a sense of cosmic helplessness. But over time, most researchers report a shift toward what might be called productive acceptance. They continue their work not because they believe they can eliminate all cosmic risks, but because they've learned to find meaning in the effort itself. Each new asteroid catalogued, each improved detection algorithm, each successful test of deflection technology represents a small victory against cosmic indifference. The psychological literature on existential risk suggests that humans are remarkably adaptable when it comes to living with abstract threats. We've learned to function despite knowing that nuclear weapons exist, that pandemics can spread globally within weeks, that climate change poses long-term challenges to civilization. Cosmic impact threats represent just another layer in this complex architecture of modern anxiety. But there's something uniquely humbling about cosmic threats that distinguishes them from human-made dangers. Nuclear weapons exist because we created them. Climate change accelerated because of our industrial activities. Pandemics spread faster because of our global transportation networks. These are problems that human intelligence created, and therefore problems that human intelligence might solve. Cosmic impacts, by contrast, represent forces that dwarf human agency. They remind us that we exist within natural systems far larger and more powerful than anything we've created. No amount of technological sophistication can eliminate the possibility that a comet from the Oort cloud might begin its journey toward Earth tomorrow, arriving decades or centuries hence with irresistible momentum. Yet there's an undeniable beauty in these cosmic processes that transcends their potential for destruction. When we observe 3I Atlas through our telescopes, streaming its delicate tail of sublimated ice across the darkness, we're witnessing artistry on a scale that no human creation can match. The impact craters scattered across planetary surfaces throughout the solar system tell stories of cosmic encounters that span billions of years. Each crater is a fossil, preserving a moment when two worlds briefly touched in the vast emptiness of space. The perfectly circular rim of Meteor Crater in Arizona, the multi-ring structure of the Chicxulub crater buried beneath the Yucatan Peninsula, the ancient scars on the moon's surface that remain unchanged by weather or erosion, all represent a form of cosmic sculpture created by forces beyond imagination. There's poetry in the fact that these destructive events also serve as agents of creation and change. The Chicxulub impact that ended the age of dinosaurs also created the environmental conditions that allowed mammals to flourish and eventually give rise to human consciousness. Without that cosmic catastrophe 66 million years ago, we wouldn't exist to contemplate the very forces that made our existence possible. Impact events deliver more than just energy to planetary surfaces. They also bring exotic materials from the depths of space, enriching the chemical diversity of worlds they strike. Many of the precious metals in Earth's crust arrived via asteroid impacts long after our planet's formation. The gold in your jewelry, the platinum in your electronics, the iridium that marks the boundary between the Cretaceous and Paleogene periods, all represent cosmic gifts delivered by violent but ultimately creative processes. Some scientists speculate that life itself might have arrived on Earth via cosmic impacts, carried in the protected interiors of asteroids or comets that survived atmospheric passage. This hypothesis, known as panspermia, suggests that the same forces we fear as harbingers of destruction might actually be the universe's method for spreading life between worlds. The organic compounds detected in comets and asteroids support this possibility. These objects contain amino acids, the building blocks of proteins, as well as other complex organic molecules that form the foundation of biological chemistry. When these materials are delivered to planetary surfaces through impact events, they provide ready-made ingredients for the emergence of life. Even if life on Earth arose independently, cosmic impacts have played crucial roles in its evolution. The mixing of materials caused by large impacts creates new chemical environments where novel forms of life can emerge. The environmental pressures created by impact events drive evolutionary adaptation, pushing life to develop new strategies for survival that increase its overall resilience and diversity. One of the most remarkable aspects of our growing cosmic awareness is how it democratizes wonder. You don't need advanced degrees in astronomy or access to professional telescopes to appreciate the significance of objects like 3I Atlas. The basic facts of its journey, its ancient origins, its harmless passage through our solar system, are accessible to anyone with curiosity about the universe. This accessibility of cosmic wonder stands in stark contrast to many other frontiers of human knowledge. Quantum physics requires mathematical sophistication that few people possess. Genetic engineering involves biological concepts that take years to master. But the story of an interstellar comet racing through our solar system at incredible speeds connects immediately with our innate sense of scale, movement, and time. Children often grasp the significance of these cosmic visitors more readily than adults, perhaps because they haven't yet learned to limit their sense of possibility. Show a child images of 3I Atlas, explain that it's older than Earth and has travelled from another star system, and you'll likely see their eyes widen with genuine awe. They understand intuitively that they're encountering something profound, even if they can't articulate the technical details. This natural human capacity for cosmic wonder suggests something important about our relationship with the universe. we seem to be naturally equipped with the ability to appreciate scales and processes that far exceed our direct experience. Perhaps this capacity evolved as a side effect of our intelligence, or perhaps it serves some adaptive function we don't yet understand. The shared experience of cosmic wonder also creates unexpected connections between people who might otherwise have little in common. An amateur astronomer in suburban America and a professional researcher in Chile both feel the same thrill when observing a newly discovered comet. A child asking questions about space person reflecting on their place, and an elderly both participating in the cosmos are in the same fundamental human activity. To understand our cosmic the attempt context, social media and global communication networks have amplified this shared wonder, allowing people around the world to participate collectively in cosmic discoveries. When images of 3i Atlas first appeared online, they were shared by millions of people who had never met, discussed, and appreciate but shared a common fascination with cosmic visitors. This global community of cosmic awareness represents something genuinely new in human history. Never before have so many people had access to real-time information about objects and events occurring on cosmic scales. We can watch solar flares erupt on the sun's surface, track asteroids as they approach Earth, and marvel at images of distant galaxies captured by space telescopes, all from the comfort of our homes. Even as our technological capabilities expand and our understanding of cosmic processes deepens, fundamental mysteries remain. Why Atlas exemplifies this persistence of the unknown. We can measure its speed, estimate its size, analyze the composition of its coma, and predict its future trajectory with remarkable precision. Yet we know almost nothing about its origins. Where exactly did this ancient wanderer begin its journey? What stellar system gave birth to the materials that comprise its nucleus forces EJ? What ected it from its original deering through inter-orbit and sent it one stellar space? These questions may remain unanswered forever, lost in the deep history of galactic evolution. And so we return to where we began, with 3i Atlas racing through our solar system at 130,000 miles per hour, carrying its ancient secrets from the depths of interstellar space. This gentle wanderer has taught us something profound about the nature of cosmic threats and the remarkable circumstances that allow life to flourish in an apparently hostile universe. The real nightmare was never the interstellar visitor announcing itself with brilliant comas and streaming tails. The real nightmare is the invisible arsenal of objects we haven't found yet, the dark wanderers following Earth-crossing orbits, the cosmic lottery that continues to spin with each passing day. Yet in contemplating these vast forces, we've discovered something unexpectedly hopeful, that consciousness itself might be the universe's greatest achievement, a fleeting pattern of organization capable of understanding and perhaps even defending against the very forces that created it. As 3i Atlas continues its eternal journey back into the cosmic darkness, it leaves us with a gift more precious than any threat it might have posed. It reminds us that we are not separate from the universe, but woven into its deepest processes, temporary arrangements of stellar matter capable of wonder, discovery, and perhaps most importantly, the capacity to protect the fragile miracle of life itself. But our cosmic story is far from complete. While 3i Atlas may be harmless, there are other visitors from the depths of space that challenge everything we think we know about interstellar objects and their true intentions. Perhaps it's time we examined the mounting evidence that suggests these ancient wanderers aren't quite as random as they appear to be.